Professor, can you hear me?
Yeah, can you hear me okay?
Yep.
Awesome. All right. Here. All right. We are ready to roll here. All right. Hello, good morning, everybody. I hope you are all doing well. Happy Thursday, almost Halloween weekend. Hopefully you guys have something fun planned. I don't know if I mentioned this on the first day of class, but I grew up in Salem, Massachusetts, which is obviously the Halloween capital of everything. And while the craziness of Salem was not always my favorite, I did appreciate the fact that if you were trick-or-treating in Salem, you would always expect someone to jump out and scare you, because that is what you would do to earn your candy. Apparently out here in Western Mass, you are not supposed to jump out of bushes and things and scare children on Halloween. So not quite as fun, but still a good time. So hopefully things are exciting for you this weekend. You get to do something if you celebrate, and if not, hopefully you have a restful weekend and get some R&R through it all. So last time we were doing what's called the product rule, which for us, the product rule is when we had two functions multiplied together. How did we approach taking that derivative? And so today we are going to be reviewing sort of the sibling of the product rule called the quotient rule. So we talked about what if functions are multiplied together, and now we're going to talk about what if we have a quotient, one function over another one. So I am going to go ahead and switch over to the DocCam. So everything printed a little small today, which I didn't realize in time, but I put everything on a book to hopefully make it a little bit bigger, but I will rewrite the functions we're working on so you can see them a little bit better. So when we talk about the quotient rule, our premise is that we're trying to take the derivative of a quotient. So a quotient is when you have something divided by something else. So like when you do like 1 divided by 4 as a fraction, that's a quotient, right? But we can also do that with functions. So if you have one function over another function, that is a quotient. And therefore, if we're thinking about how to take the derivative, we need to use the quotient rule. So just like the product rule, we can't just take the derivative of the top over the derivative of the bottom. And we've sort of hinted at this because remember before when we were thinking about functions like 1 over x cubed, we couldn't take the derivative like that. We couldn't just take the derivative in the bottom. We would have to rewrite it first, right, before we could take the derivative. So here, the same idea applies. We can't just do f prime over g prime. Instead, we do have a formula that comes out from looking geometrically at derivatives. We won't go through that, but it's a little bit interesting. If you're interested, you could easily Google it. But we get a formula for the quotient rule, just like we have a formula for the product rule that we will apply whenever we see this type of function. And so our formula says we're going to take the derivative of the top times the bottom minus derivative of the bottom times the top, all divided by the bottom function squared. Okay, so sometimes you'll see the formula fully written out like this. Sometimes you'll see it abbreviated f prime g minus g prime f divided by g squared. Those mean the same thing, right? It's implied that these are functions of x or of the independent variable. But one thing I want to point out here that's especially important, that's different from the product rule. So in the product rule I mentioned, it didn't matter how you picked your f or your g, that it could be either one, but the convention is that the first thing we see is f. In the quotient rule, it does matter. Okay, in order to apply this formula, we always call the top function f and the bottom function g. And so that makes a difference because the operations that we're doing here are subtraction and division. So the order does matter. So when we set this up, we're going to set it up pretty much the same as the product rule where we're going to identify F, we're going to identify G, we'll take each of their derivatives, and then we'll plug it back in. But when we pick our F, it always has to be the top function. Okay, so let's start with an example so we can see how to apply this. So I'm going to write this just a little bit bigger. So our function here that we're going to look at is e to the x over x to the fifth. Okay, this may look familiar to you because remember the last problem we did last time was this problem, but we turned it into a product rule. We said, okay, how about we turn this into a product rule and apply the formula? And we did that by bringing the x to the fifth up. But now we're going to do it again, but we're going to do it as a quotient rule to see how to apply this formula. Okay, so again, when we do the quotient rule, what we're going to do is we're going to pick our top function to be our f in our side work. So my f here is e to the x, and my g here is x to the fifth. So once I've separated the top and the bottom, I want to find each of their respective derivatives. So we know that the derivative of e to the x is e to the x. The derivative of x to the fifth is 5x to the fourth. Okay. Once we have those pieces, we're going to plug everything back in to the quotient rule. So we're going to do f prime times g. So we have e to the x times x to the fifth minus g prime times f. So 5x to the fourth times e to the x, all divided by g squared. So x to the fifth squared. Okay, so this is what our derivative looks like. Now, we could theoretically change our x to the fifth squared into x to the 10th, because if you have a power raised to a power, you can multiply them together. However, conventionally, we don't simplify this. Every once in a while we do for one reason or another, but typically we don't. We typically leave it as g in parentheses squared. So there's a lot of simplification we could do on this, but that's not the focus right now because I want to get you used to the quotient rule. So setting it up and just making sure you have the terms in the right place is what we're really going to be practicing today. Okay, so now that we've seen one in action, let's look at another one that's not overly complicated. So here I'm just going to write this a little bit bigger. So f of x equals sine x over ln x. Okay, so what I want you to do is I want you to take about 2 minutes and see if you can work out the quotient rule on this and what your final derivative will look like by using this formula. Okay, so take 2 minutes. Feel free to work with someone next to you if there's someone next to you, or refer back to your notes, of the basic derivatives if you need to, but we'll go over it together in about 2 minutes.
Yeah, any questions at the time, raise your hand and say them. You want to seems like you're on there. Have any questions?
All right, take about 30 more seconds. All right, so let's go over this. So again, the first thing we need to do is we need to recognize that this is in quotient rule form. So we see that we have one function over another one. So we think quotient rule. And so now we want to set this up where our top function is our f and our bottom function is our g. So again, that order is important. Now we want to take each of their respective derivatives. The derivative of sine is cosine. The derivative of natural log of x is 1 over x. So now that we have all our pieces, we have to plug it back into our quotient rule formula. So we're going to do f prime times g. So here we're going to have cosine x times ln x minus g prime times f. So 1 over x times sine x, all divided by g squared. So again, we're going to write our g in parentheses and then square whatever that was. So here, again, the idea is that we're breaking up our quotient into their individual pieces. Hopefully we can then take their derivatives and then we're assembling it back together using this quotient formula. Okay, so hopefully that made sense. And then obviously once we do that, there's a whole bunch of other applications we can do, which we will try out now. So first, sort of our common example, find the equation of the tangent line. And again, I'll write this function a little bit bigger up here. So we have the natural log of x plus 2, all divided by x cubed. Okay, so we want to find the equation of the tangent line at x equals 1. Process is the same as we've always done for tangent lines. We need a point, we need a slope, we need to put it together to get the equation of a line. The difference here is that when we find our derivative, in order to talk about the slope, we're going to be doing a quotient rule. Okay, so I'm going to give you another 2 minutes to try this one out. Again, process is the same as we've been doing for all of the equation of the tangent lines. So give it a try and then we'll go through it together. All right, take about 30 more seconds. All right, so again, for the equation of a tangent line, we need a point and a slope. We have half a point, so to get the y value, we need to plug the x value back into the original function. So here, if we crunch all these numbers, the natural log of 1 is 0, plus 2 divided by 1, it's going to give me a value of 2. So when x equals 1, y equals 2. So the point is 1, 2. So that's half of what we need. The other half is the slope, which we get from the derivative. So here, to find the derivative of this function, we're going to need to do a quotient rule because we have one function over another one. So again, the top part of our function has to be our f. And the bottom part of our function is going to be g. We separate those out. Now we want to find each of their respective derivatives. So here the derivative of the natural log is 1 over x, and the derivative of 2 is 0 because 2 is a constant. So now here the derivative of x cubed, we get 3x squared. So plugging everything back into our quotient rule formula, we're going to do f prime times g, so 1 over x times x cubed, minus g prime times f, and I'm going to use parentheses because there's more than one term, all divided by g squared. Okay, so we do have to plug a 1 into this to get our slope. And I will tell you, it's up to you whether or not you want to simplify first, right? We could simplify this term. We could simplify this term. Sometimes it helps to simplify before you plug a value in, but it's really up to you what you prefer, right? You don't have to simplify. You can just plug in 1 as is. It's really a matter of preference. So if we don't simplify, we have 1 times 1, which is 1, minus 3 times 1 squared, which is 1, times the parenthesis. So the natural log of 1 is 0, plus 2 is 2, all divided by 1 cubed is 1, and then 1 squared is 1. So then when we crunch all these numbers, we have 1 minus 6 divided by 1. So 1 minus 6 is -5. -5 divided by 1 is -5. So now we have a slope. Remember, when we find the derivative, that's going to give us the slope of the tangent line. So we take our point and we take our slope, and we're going to put it together in y equals mx plus b. Let's see. I guess we'll just write right on the index card. So y equals mx plus b. We know that our slope is -5. So we have y equals -5x plus b. Now to find our b value, we need to plug in our point. So when x is 1, y is 2. So we have 2 equals -5 times 1 plus b. So this gives us -5. So we have to add that 5 over to the other side. And that gives us that b will equal 7. Putting everything together, we get y equals -5x plus 7. So again, the process of finding the equation of the tangent line is the same. What's changing is the function, right? And so here we have to apply the quotient rule, but as long as we do that carefully, we can then plug in our x value to get our slope and put it all together to get the equation of our tangent line. So again, this is a common example you can expect to see on your chapter quiz and in other applications we do later in the course. So it's good to get used to this idea of the equation of the tangent line. So let's look at our next example here. We want to find the first and second derivative of x to the fourth over sine x. So I'm just going to write this a little bit bigger. X to the fourth over sine x. So when we do this out, our first derivative, we're just going to be using the quotient rule. We see one function over another one. However, in order to get to the second derivative, we are still going to have to use a quotient rule, but then we are also going to need to use things like the product rule and the chain rule. So the second derivative is a bit complicated on this, but I want you to try it. I'm going to give you a little more time just because the second derivative uses so many of the other things we've been talking about. But I want you to give it a go. So do your best to definitely find the first derivative based on what we've been doing, and then see if you can figure out all the things we need to use to find the second derivative. You can obviously look back in your notes for the product rule and the chain rule if you need to reference that. But I'm going to give you about 4 minutes to try this out, see how much you can figure out, and then we'll go through it together. All right, take about 30 more seconds. All right. So we're going to need a lot of space to write out a lot of our pieces here. So again, on first glance, I'm thinking, okay, I have one function over another one. I need to use the quotient rule. So to get to the first derivative, I'm going to use the quotient rule. And again, the top function is going to be our f, and the bottom function is going to be our g. So the top function is x to the fourth, and the bottom function is sine x. Then I want to find each of their respective derivatives. The derivative of x to the fourth is going to give me 4x cubed, and the derivative of sine is going to give me cosine, right? So to get my first derivative here, I just need to plug this into my formula. So I'm going to have f prime times g, so 4x cubed minus g prime times f. I'm going to write the x to the fourth first, since that's the convention, all divided by g squared. Okay, so the only sort of weird thing I did is I switched the order of x to the fourth and cosine. Since they're multiplied together, it doesn't matter which one we write first, and typically we write the polynomial term first. But this is what our first derivative looks like. And so our first derivative is pretty much in line with the other first derivatives we've been doing for the quotient rule. Where things get tricky is when we try to take this first derivative to go to the second derivative, okay? So here, you'll notice that our top function is much more complicated, right? Before it was x to the fourth. Now when we talk about the top function, it's the entire numerator, right? So here, because I'm going to need a lot of space, my top function, we have 4x cubed times sine x minus x to the fourth cosine x. And my bottom function, which is my g, is sine of x squared, okay? So here I just, again, split them up into f and to g. Now looking at each of these, the first one, I notice that I have things that are multiplied together. So I'm thinking there's going to be some product rules in here. Over on my g function, I notice that I have parentheses raised to a power. So that actually should signal me towards the chain rule. So again, the variable's in the base and it's all raised to the power. So I'm actually going to do g prime first, and then we'll come back and look at the derivative of f. So with the chain rule, when you have something in the form of a power function, the rule says we can bring the power down, everything inside stays the same, and we subtract 1 from the power. So that's the first part. The 2 comes down, we subtract 1 from the power. But then in the chain rule, we have to remember to multiply this by the derivative of the inside. And so the inside here is sine. So the derivative of sine is going to be cosine. So that's the chain rule here that's going to give us the derivative of g. Now for f, I'm going to split this into two pieces, right? Here's the first term, and here's the second term. So starting with the first term, I'm going to put a 1 here. I notice that I have 4x cubed times sine of x. So again, I notice that there's an x in both terms. I notice that I can split them up into a left side and a right side. So I know that I need to do a product rule here, okay? And so I'm going to do this on the side. So when I do my product rule, my first function is my f, 4x cubed. My second function is my g. Then I take each of their respective derivatives. The derivative of 4x cubed is 12x squared. That's a power rule. Derivative of sine is cosine. So when I do the product rule here, I do f prime times g plus g prime times f. So for this first part, f prime times g is going to give me 12x squared times sine x plus g prime times f, so 4x cubed times cosine of x. Okay, so that's that first part. And remember, this is the first part of our derivative. So this, the derivative of this first term results in this here. Now I also need to subtract off the derivative of this second term. So notice again, with the second term, I again have a product. I have something times something, right? And I can easily divide them, so I know it's a product rule. So again, I'm going to do the product rule over here on the side in my notes. So my f is x to the fourth. My g is cosine x. F prime is the derivative of x to the fourth, which is 4x cubed. Derivative of cosine is negative sine. So now again, I need to do f prime times g plus g prime times f. However, I want you to notice that this was a minus. Since we subtracted off this entire term, we have to subtract off the entire product rule here. So I'm going to use parentheses and then put my derivative in the parentheses. So f prime times g, so 4x cubed times cosine x plus g prime times f. So there's a negative here. I'm going to pull that to the front. Negative x to the fourth sine x. So that is the derivative of the second term. Okay, so again, I split the f term into two terms. I had to do a product rule for each one. And now I have all my pieces, right? I have f, f prime, g, g prime. And now I have to put them all together in my quotient rule. So I'm actually going to grab another piece of paper. So I have enough space to write everything down. Okay. So these are the four pieces I need now. I need my f prime, g, g prime, and f. So again, this is all to find the second derivative. And so the quotient rule says we're going to do f prime times g is the first part. F prime is really long, so I'm going to use brackets just because there's already parentheses in here. So I have 12x squared times sine x plus 4x cubed cosine x minus 4x cubed cosine x plus negative x to the fourth sine x. That's my f prime. So then I close the parentheses times g sine x squared minus, now I have to do g prime times f. So g prime, we have 2 sine x cosine x times, now notice I'm going to run out of space again, so I'm going to write it underneath. So times f, so 4x cubed sine x minus x to the fourth cosine x. Okay, so that is multiplying this term, and that is all divided by g squared. So g is already squared, so we have to square it again. So sine x. So if we have sine x squared squared, that becomes sine x to the fourth. So again, this is not trivial, right? The first derivative that we did here was using the quotient rule. It was pretty, standard for a quotient rule. But to get to the second derivative, all of a sudden we have product rules, we have chain rules, we have super long terms and things that, we have to be careful about writing everything out. Can we do it? Yes. Does it take a long time? Also, yes, right? So we have to be very, very careful and make sure that we're writing out all our pieces as we go. Why? Because if somehow we go back and we enter it and it's wrong or something like that, we want to be able to check each term against the work we did, right? Because maybe it was a transcription error. This is not a common quotient rule problem. Obviously, this is quite a bit harder than your standard one, but it does bring in everything we've learned in this class in chapter 3. So it, certainly is able to test that you are able to do the product rule, the quotient rule, the chain rule, all the, basic derivatives, and put them all together to get a final solution. Okay. So again, it's hard, mostly because it's long, but if you're careful and you write everything out, you can certainly get to the final answer. Okay. All right. That being said, let's look at, find where I put the next one. Okay. So without being quite as difficult, we can certainly look at examples where we need to do other things like the chain rule within a problem. So again, let me rewrite this a little bit bigger. Sine of x cubed plus 2x minus 1 divided by e to the 5x cubed. Okay, so here we have another quotient rule. We have one function over another, but you can see that embedded within this quotient rule, we definitely have some chain rules. So for this one, we're just looking for the first derivative. So it actually won't be quite as long as the last problem, but we do have to employ some chain rules within this to get to our answer. Okay, so I'm going to give you about 3 minutes to try this one out. Again, feel free to look back in your notes to the chain rule if you need to reference those, but carefully make sure you write out all the pieces and then put them back together carefully. So we'll go through it together in about 3 minutes. All right, take about 30 more seconds. All right, so let's go over this one. So again, one of the key things we're really doing here is just recognizing that we're using the quotient rule, but we see that we have one function over another one. And so we think, okay, quotient rule, and our top function will be our f, and our bottom function will be our g. So here, the next step is to take their derivatives, but I see that for both of them, I'm going to have to use a chain rule. So for the first one, I see that I have sine of something complicated. And so our chain rule says, okay, you're going to change the outside function. So sine turns into cosine. When we do that, the inside stays the same. But then we have to remember to multiply that by the derivative of the inside. So we're looking at the derivative of x cubed plus 2x minus 1. I'm going to use parentheses because there's more than one term. So here the derivative of x cubed is 3x squared. The derivative of 2x is 2, and the derivative of 1 is 0. So my f prime looks like that. And then for my g prime, I again notice I have a chain rule, but this is the exponential form. So I have e raised to 5x cubed. I notice that the variable's up in the power. And so for exponential functions, especially e's, I'm going to get the same thing back, e to the 5x cubed times the derivative of the power. So here, the 3 comes down to multiply the 5, and I get 15x squared. So the real hard part in this is finding these two derivatives within the problem. Now that we have them, we can plug these into the formula for the quotient rule. So we're going to do f prime times g. So I have cosine of x cubed plus 2x minus 1 times 3x squared plus 2. That's my f prime times g, which is e to the 5x cubed minus, now I'm going to do g prime times f. So e to the 5x cubed times 15x squared times f, which is sine of x cubed plus 2x minus 1, all divided by g squared. So e to the 5x cubed squared. So again, typically we leave whatever's in the function the way it is and then squared. We don't usually square it out. So you are most likely to see an answer sort of written like this. So again, depending on how you order your functions, right, we have to do f prime times g minus g prime times f. But like f prime times g, it doesn't matter if the e term comes first or the cosine term comes first. So if you're looking at an answer and trying to figure out if it's the same as your answer, you really just want to look at each factor and make sure that each factor is in the first part of your answer. So you're going to look and say, does it have a cosine of x cubed plus 2x minus 1? Yes. Does it have a 3x squared plus 2? Yes. Does it have an e to the 5x cubed? Yes. Okay, so the first term looks good. And then you'll do the same thing for the second part, right? The minus part. You're going to look at each piece or each factor and make sure that that's in the answer, and then also check the denominator so that, you know, if the 15 was in the front, right, you don't want to pick the wrong answer because the 15 wasn't in the same place you wrote it down as. So check each term to make sure that each term is in the answer. Okay, so that's our last example today for the quotient rule. I'm going to let you guys go because it's sort of a light week to help the whole mid-semester craziness that's going on. So again, try the homework on the quotient rule before you do the quiz for sure. And definitely stop by the review tonight with William to go over all the derivatives if you can, so that you're prepared for Monday's quiz. Okay, have a great rest of your day, and I will see you guys all next week.
Thank you.